All right, we got about a minute before the official start time of the lecture. So I'm just taking a look at the text screen of Discord and see if we have any questions. Okay, Daniel says nice. Okay, very good. Did you know that nice is a Linux command? It makes a process nice, as the name implies. Yeah, and there's also re-nice, if I remember correctly. Let me just kind of type it. Yep, there's a command called re-nice. So there's nice, and then there's re-nice. Make something nice again. So that's an interesting one. All right. Yeah, you can basically change the priority of a process using the nice command. So the idea is you lower the priority using the nice command. So this way, if you have anything that takes a lot of computation power, it will only execute when there's available processing power, and it's not going to hog processing resources from other processes, that are in the foreground. So and then re-nice, changes the priority once it has started. I think nice starts it, and then re-nice can change it. So that's a very interesting command. All right. So what we'll do today is going to be interesting, to say the least, because we are going to talk about addition. We are going to relearn addition, how to add two values all over again. Okay. So this is going to be interesting because one half of the class is going to be, most people will look at this and go like, why are we even talking about this? And then the other half of the class, in terms of class lecture duration, it's going to like, I have no idea what you're talking about. So we'll get to see both sides of addition today. All right. So this is where we are at this point, just in case for those people who did not review any material over the weekend, the long weekend, 5 days. This is what we are doing. Time to be on both sides. Yes. So hopefully we'll be on both sides at the same time. We know how to make a connection from things that are really obvious that we are used to things that are just kind of new, but should not be that big of a leap. Okay. So where we are at this point is we are now done with values, numbers, and bases. And today's lab is for base conversion. And then at some point, I will disclose today's row-taking passcode. Okay, so, well, okay, I'll be kind for those people who do not have time to watch through the entire lecture just to find out what the word is. The word is ripple, R-I-P-P-L-E, okay? So ripple is the word of the day, and there's a reason why it is the case, because we'll talk about carry ripple adder as we continue today's lecture. Okay, so knowing that this is where we are located, and I'm really hoping that most of you have found some time over the weekend to read ahead of me so that you know what we are going to talk about: binary number addition. Okay. So the module looks like this. Okay, I made some minor tweaks, but it's not major. So by the time we get to the tweaks, I'll explain it. Okay. And Daniel is typing something. I'll keep an eye on that. All right. So ripple, yes, that is the keyword of the day for row-taking purposes. So go ahead and do it now, okay? Since Daniel just kind of typed it up on Discord, why don't the rest of you all go to the row-taking activity and just type in ripple, press enter, make sure you get that point, and be done with it. Okay, we got Mustafa and Aiden typing. And we just have Mustafa typing right now. All right, so we'll go ahead and we'll wait for Mustafa's question, and I'm gonna set up a few things over here. Let me see what would be the best way to do it today. I think a plain text file will work, so I'm gonna do that part here. All right, so Mustafa typed, I accidentally typed something before the class started. Why would you type something before I even talk about the word? Okay, we'll deal with that later. Okay. Well, let's not laugh. Okay, maybe we just pressed the button accidentally. But next time, please wait until I disclose the word, okay? Because the chances of you guessing the right one is pretty slim. All right. Okay, so what we'll do is we are going to start with a discussion of addition, but it's going to be in base 10, okay? So the first question is, what is 2 plus 5 in base 10? I mean, that's really obvious, right? It's 7. So how do we know this? Okay, well, that's because we have memorized the addition table since we were very, very young. Okay, so how young depends on a lot of factors. But I think most people agree that by the time we get to 3rd grade, regardless of culture, regardless of where we come from, we understand addition. At least we know how to do it in base 10. Okay, so addition is not terribly difficult until we get to the concept of carrying. Okay, so if I ask this question, okay, I'm pointing to the question here. If I ask what is 7 plus 5, okay, most people know the answer. Okay, it's like, okay, it's 12. How do we write the value of 12? It is 1 and a 2. Okay, so well, okay, so plus is the addition in this case. It's not concatenation, okay, which some languages use. Okay, so 7 plus 5 is 12. But how do we know that, right? I mean, well, that's because, when we were young, okay, most people like myself would take a class in elementary school and we get to play with blocks, okay? So there's one block that is 7 units long. There's another block that is 5 units long. And then we put those blocks, end to end to extend, the length of one, with the other one. And now we count, oh, okay, so, and then we learn the words 12, and we learn how to write the quantity as a base 10 number. Okay, so, all right, so what is the big deal? The big deal is the concept of a carry, okay? In other words, instead of saying 7 plus 5 is 12, so be careful, pay attention now, okay? I'm going to say something that that is going to sound really absolutely normal, and then later on somebody's going to ask me, can you say that again? So I'm going to say it now, okay? So pay attention. Okay, when I said those words, what is the name of the bad lion in Lion King? When I said those words, pay attention, is part of this. Yeah, exactly, Scar. So in the original Lion King soundtrack, there was a song, of Scar, singing to the hyenas, and basically, convincing the hyenas to help him with the coup, right? And part of the phrase that he sang was, "Now pay attention." Yeah, so exactly, that's exactly what I want you guys to do, but I just did something that's distracting. Okay, I apologize for that. So carrying is important, okay? Because the quantity 12 cannot be represented by a single digit in base 10. So I say that one more time, okay? So the concept of carrying, say, in one single digit. I can write the 2 as one digit as the result, but I also have a carry of 1. Which basically is saying the next digit, the digit to the left-hand side, now needs to somehow, okay, incorporate this additional 1, which to me is a 10. But to the next digit, to the more significant digit, to the left-hand side, it is really just a 1. Okay, so this is important. Do we have any questions about the concept of a carry in addition, in just base 10? So we are not talking about base 2 or binary at all. We are only talking about base 10 at this point. So do we have any questions about the concept of carrying? Okay, no questions. Very good. Then we're going to move on. So now we are moving on to binary addition. So binary addition is super easy, okay, because there are only 4 possible cases. If you think about base 10 addition, there are 100 cases because there are 10 possible digits to the value to the left-hand side of the addition, and then there are 10 digits, 10 possible digits to the right-hand side of the addition, operator. So now we have 10 times 10, which is 100 possible cases. Now, most people would point out right away and say that, well, but addition is commutative, which means a plus b and b plus a are exactly the same thing. Well, that is true. So that means we only have to memorize 1/2 of the cases. Not only that, we also have the identity of addition. In other words, if you have a plus 0, that's just a. If you have 0 plus a, that's just a too. So that eliminates, one additional row, after we cut the table in half. But it is still a pretty large number of table or items for a child at the age of 6 or 7 to memorize. Okay, that's still quite a bit. Now you're looking right here. You're looking at the entire addition table in base 2. So we'll go through this one by one and we'll see whether they make sense or not. When you see 2 as a subscript, that means I'm emphasizing that we are talking about base 2 numbers in this case. So we have base 2 0 plus base 2 0 equals to base 2 0. Does that make sense? Okay, regardless of the base, 0 is always 0. It means nothing, right? I mean, that seems to make sense. 0 plus 0 is just 0, regardless of the base. Okay, let's move on to the next item. The next item says 0 in base 2 plus 1 in base 2 is 1 in base 2. So once again, okay, the base really should not matter, right? Because 0 plus 1 is just 1, and 1 in any base that is 2 or more is just 1. Okay, it's really kind of there's no question about that, I hope. So let's see, there are no questions. Okay, let's move on. And I'm just checking Discord to make sure that it's still alive, because sometimes Discord will crash, but the window stays up, so I cannot tell that I have just lost the entire class. All right, the third case. So the third case is pretty much the second case, except I have just reversed the order. So instead of asking what is 0 plus 1, I'm now asking 1 plus 0. Since we already know that addition is commutative, so we say, okay, 1 plus 0 is just 1 too. Okay, no big deal. So now we are getting to the last case, which is the only one that is kind of like, okay, that looks a little strange, but wait, that makes sense now. Okay, so we'll take a look at this one. So 1 in base 2 plus 1 in base 2 is 1, 0 in base 2. So now the question is, why does it look so strange? Because we are used to thinking 1 plus 1 is 2. Well, that's only because 2 is a digit available in base 10 to represent the quantity of this. Okay? For those of you who need accessibility, I'm holding up 2 fingers. Okay? So the value of 2 can be represented by a single digit in base 10 because we can represent everything from 0 to 9 using a single digit in base 10. In base 2, we only have 2 digits, 0 and 1. So as a result, the value, the quantity of 2 cannot be represented by a single digit. So now we have to ask, okay, if we cannot do it with a single digit, how do we do it? Well, we get back to base conversion. So in base conversion, the digit, the 0, this particular digit here, or the least significant digit when it has no decimal points, okay? So the least significant digit is telling us how many ones we have. The digit to the left-hand side of the least significant digit, we'll call this digit 1, okay? So digit 1 is telling us how many 2 to the power of 1s we have. Oh, well, since we want to represent the quantity of 2, obviously it has exactly 1 2 to the power of 1, and that's why that digit in base 2 is a 1 when we want to represent the quantity of 2. So I'm just going to give you guys a few seconds, maybe 5 seconds, and see if there are any questions about this multiplication table that explains every single possible way to add 2 single digits in base 2. So I'm just looking at the time and count to 5. All right. So I'm not seeing any questions in the text channel. So I do have one person asking from direct message. Let me go check that out. Oh, okay, that's not related to what we are talking about here. Okay, so are we good so far? Okay. All right. So if there are no questions about why 1 plus 1 is 1, 0 in base 2, then we are going to talk about some symbols. Okay, so everything up to here is really just explaining why 1 plus 1 is 1, 0 in base 2. Okay, so what we'll do instead at this point is we are going to take a look at things in a slightly different way. Okay, we'll separate the result of an addition into 2 parts. So we are talking about this section here. So we are now separating the result of adding single digits into 2 different parts. So when we're adding x and y, the result of the addition is r, and we are only referring to a single digit as the result of adding x and y. So if we're talking about in base 10, 7 plus 5, the r of 7 and 5 is going to be 2. Are we doing okay so far with this? Because we are focusing on a single digit of adding 2 digits in a particular base. I'm going to give you guys some time in case there are questions. All right, so if there are no questions, we are moving on to the concept of a carry, also in base B. So the carry of adding x and y is looking at the actual sum of x and y. If that is greater than or equal to b, which is the base that we are dealing with, then we have a carry of 1. Otherwise, we have a carry of 0. Okay. All right. So I know this stuff here may look kind of confusing. So what we'll do is we're going to take a look at a few examples. So we'll go ahead. I'm just creating a document right now. So give me a second to create that. And it is supposed to give me a preview window somewhere. Okay, so give me a second to find the preview window because I got too many windows open and it's not here. Okay. I'm just thinking about whether I should do that or not. Okay, maybe I'm not going to do that. So what I'll do instead is I'm just going to use this as a electronic whiteboard or chalkboard, and then we'll just go ahead and use a few examples. So I'll say in base 10, okay, the R, or the single digit result of adding, let's just reuse the example that we have, okay? The example was 7 and 5. So the single digit result of adding 7 and 5 is 2 because we're focusing on only one single digit. So we are not dealing with the carry at this point, okay? And then the carry of adding 7 and 5 in base 10 is 1. So are we doing okay so far with this notation? I'll give you guys another example. So if we add 3 and 4 in base 10, then the single digit result is really just a simple 7, but the carry is a 0. So when we add 3 and 4 as single digits in base 10, the carry to the next digit is a 0. So instead of saying there's no carry, we will now change how we name it and say that we have a carry of 0. So we got Aaron P typing, so we'll go ahead and wait for that question. Yes, absolutely.
Okay, so just to clarify, so we're carrying to the left. It's like the tens and then the
Yes.
hundred.
Yep.
Okay.
Yep. Exactly. All right. So, Aaron, do you still have a question, or are you good? Okay. All right. Excellent. So this is all in base 10. So now let's go take a look at what happens in base 2. Okay. So, oh, before we move on, okay. So this is one thing that is kind of important, even though it doesn't look like it's important, is we want to be able to generalize. Okay, we want to come up with a generalized definition of R and C, of a particular base B, so that we can at least mathematically understand what it is, and then we can apply that directly when we are going to talk about base 2. So in base B, okay, so B is now a variable. So Rxy, which is the single digit result of adding the digit x and digit y in base B, it really is quite simple. It is just x plus y, look at the actual value of the sum, and then you mod it with B. Okay? And then the carry, okay, is also relatively easy to understand. It is x plus y, okay, looking at the value of x plus y. And then we check whether it is greater than or equal to b. If it is the case, then we say the carry is a 1. If not, we say the result of the carry is a 0. So does anyone need an explanation of what the question mark and the colon are doing in an expression, or do we all remember what is ternary operator? Because I want to see if I can make that assumption. If you do not want me to make that assumption, you need. Okay, all right. So ternary operator is like this. Okay, so it has got 3 parts. Okay, so the value of this expression. So we'll call the first one A. Okay, A question mark B colon C. Okay, is B if and only if A is true, C otherwise. Okay, so does that help? A is a condition. If and only if A is true, the value of the entire ternary expression is B. If and only if A is false, the value of the entire ternary expression is C. So we're good? Okay. So it's not quite a statement, okay, to be exact. It is not quite a statement. It is an expression. But it does have the effect of an if-then-else statement. But it really is just an expression, which makes it even more fun because an expression can be a part of any expression, right? So you can put this, as a part of a condition. You can put this as as an argument that you're passing to a subroutine, and so on and so forth. So ternary expression is actually a very handy feature, and most programming languages now have it. It's not just C and C++. Even spreadsheets have it. Okay, there's a if-then-else in most spreadsheet formulae. All right. Cool. All right. So does that make sense? This generalized definition of what R and C look like in any base. Well, first of all, we want to reapply that to the examples in base 10 and see if it makes sense, right? So let's plug it into here, okay? So we'll plug the equation into here, and then we plug in the definition of R, which is, in this case, 7 plus 5 mod 10. Because in this case, we're dealing with base 10. So we have 12 mod 10. 12 mod 10 is the remainder of 12 divided by 10, which is actually 2. Let's look at the carry. 7 plus 5 is greater than or equal to 10, question mark 1, colon 0. Okay? So 7 plus 5 is 12. 12 is greater than or equal to 10, and as a result, 1 is the value of the entire ternary expression. So it does work out in base 10. So are we good so far? How we applied the abstract version of R and C with base B back to the examples that we have talked about in base 10. So are we good with that? Okay, so we're good. Excellent. Thank you for the feedback. So now what we're going to do is we're going to move on to base 2. So when we apply R and C to base 2, it's not mysterious, right? So in base 2, R x y is x plus y question mark, percent 2, mod 2. And then cxy is kind of the same thing. X plus y is greater than or equal to 2 because our base is 2 in this case. Question mark 1 colon 0. Okay, so that's really not really surprising because all we did was to replace b, lowercase b, with a literal value of 2 because now we are focusing on base 2. Okay, but what we can do now is to look at a table. So we use a truth table where we have x, y as independent variables, and then we look at r, x, y, and then we look at c, x, y. And this table is going to have how many entries? There are 2 possible values to x, and there are 2 possible values to y, and they are fully independent, which means we now have 4 rows. So x can be 0 or 1. And while x is 0, y can be 0 or 1. While x is 1, y can be 0 or 1. So now we apply that. What is R 0, 0? The result of the single digit result of adding 0 to 0 is pretty easy. It's just 0. The carry is also just 0 because the sum is 0 and 0 is not greater than or equal to 2. Moving on to the next one. Okay. 0 plus 1. The single digit result of 0 plus 1 is just 1. And the carry of 0 plus 1 in base 2 is a 0 because 0 plus 1 has a value of 1 and 1 is not greater than or equal to 2. The next one is the same thing because we know that addition is commutative, so it's the same idea. And this is the only row that is kind of remotely interesting because the result of 1 plus 1 in base 2 is 2 mod 2. The remainder of 2 divided by 2 is a 0. And then the carry is 2 plus 2 is greater than or equal to 2, which is true. So we have to take the middle value, which is a 1. So it does have a carry of 1 when we are adding 1 to 1 in base 2. So are we good so far? Are we understanding this table? Excellent. Okay, very good. So we are just zipping along. Okay, excellent. That is good. So we look at this and go like, well, but that's not very helpful because this is not, we cannot do this using transistors because remember, we're trying to convert everything that we can do into something that transistors can do because transistors are real devices. We can use transistors to make computers. So we want to look at operations that we need to perform, and addition seems to be pretty elemental to what a computer should be able to do. So we want the computer to be able to do this using transistors. So we look at this and go like, wow, this is really complex, okay? Because we got addition here, we got a mod operation, and mod operation implies there's a division. And division, as you already know, is the last of the 4 basic arithmetic operators that we learn. We first learn how to add, then we learn how to subtract. Only after that we can learn what is, well, only after addition we can learn multiplication, and then division is the last one because division has implied multiplication, comparison, and also subtraction in it. Okay, so we cannot learn division until we know how to do subtraction. So these are not simple operations. So now we look at this truth table and then we look at this and go like, can we do this in a different way? Okay, now the obvious answer is yes, right? So we'll focus on the easy one first. Okay, so I'm gonna do the laziest thing ever. Well, not ever, but lazy thing. So we'll get rid of the R column so that we can focus on the C column. Okay, so we look at this and we ask, Well, if this is what we really need, exactly. So Daniel has got it. Okay. So when we look at this, we say, hey, we don't need no stinking comparison. We don't need no stinking ternary expression, because a simple and is going to do this. Okay. So we say x and y. Okay. So we look at x and y as a column. 0 and 0 is a 0. 0 and 1 is a 0. 1 and 0 is a 0. 1 and 1 is a 1. Woohoo! Done. Oh, but wait, Tech. You mentioned something about using transistors to do it, right? So now the question is, can we use transistors? Not one, but as many transistors as it takes. Can we use transistors to compute x and y? Well, it would take 4 transistors to make a NAND gate, and a AND will take 2 NAND gates. So if we do it the clumsy way, okay, if we do not optimize and do it the really clumsy way, we'll need 8 transistors to do this. But the point is, we can, okay? The point is, yes, we can use transistors instead of using comparison or the ternary operator. We can use transistors to implement the C function when we just want to perform single-digit additions in base 2. Woohoo! Wow, this is, I mean, I agree with Tom. You know, this is a big wow, okay? Because we are now converting arithmetic operations into bitwise or logical operations. And we know that transistors can do bitwise or logical operations. So this is good. So now we focus on the other one, okay? So the other one is not as cooperative, okay, which is the R function. So now we have to look at this and go like, how are we going to do something like that? Because it is not exactly an OR, okay? Because if it were an OR, then the last row would also get a 1 as a result. So it's not quite an OR. It is called exclusive OR, okay? So X exclusive OR would do exactly the same thing. So we can say X exclusive OR Y. Now there are 2 ways to spell out exclusive OR. In some textbooks, they use XOR for exclusive OR. And in other textbooks, they would use EOR for exclusive OR. So both are fine, okay? We don't have a particular symbol to represent exclusive OR. Not one that I can type easily using a text editor, okay? All right. But then somebody is going to say, but Tech, you never mentioned anything about implementing exclusive OR using the NAND gate, right? Okay, fine. You know, you caught me. So let's not use exclusive OR. So now the question is, without using exclusive OR, using only the logical operators that we have defined so far, which is really just negation, conjunction, and disjunction, how do we emulate the same result as exclusive OR? Well, that's actually a pretty easy way to think about this. The easy way to think about this is to ask, what kind of expression will give me a 1 for this particular row? In other words, when x is false and y is true, what expression will be true, but only in this specific case? So we now say, well, we can negate x first, and then we can use that to AND y, okay? So I'm using a shorthand now, you know, not xy. Is not negating x and y, it is negating just x. The negated version of x is ANDed with y. All right, fine. I'll give you the super longhand to understand this one. Not x is one term, y is the other term. And remember, in notation, I borrow multiplication to mean conjunction, and that's why, you know, in the shortest form, it is not x, y. Is that answering any question? Okay, that's all good. What about the next one? The next one has x being true and y being false, but I want to come up with an expression That is true, but only for this row. Okay, it will be false for any other row. Okay, so we say, well, we can do something like this. Okay, and that in the longer form using all the parentheses and the extra operators is really x and not y. Okay, so is everybody convinced that not x and y will give us a 1, but only for the second row? X and not y will get us a 1, but only for the third row. Because if you apply these two expressions to any other rows, okay, other than the rows that they are on at this point, they will give us a 0. They will give us a false. Okay, so now I look at these two rows, and then I say, hey, if I do an OR of these two expressions, then the OR will be 1s for the two rows where I need the result to be 1s, but it will still be 0s for the other two rows. Okay, so instead of saying that, I'm going to give you the actual formula. I'm going to use the shorthand because you guys really need to understand the shorthand. So I'm going to use the shorthand here. So I'll give you the shorthand something like this. And now we have an immediate question is, what about the order of these operators? You did not use parentheses to tell us whether the disjunction, which is represented by a single plus here, whether that should take place before or after the conjunctions. So what about the ordering? We are using the same operator priority as in normal arithmetics. In other words, if I do not use parentheses, you perform the negation first. So negation has the highest priority, the exclamation point. The next one is going to be the multiplication, which in this case is a conjunction. And then the least one, the lowest priority, is the disjunction, which in this case is represented by the plus. In other words, okay, I'm not going to use this longhand much longer. But if you do want me to convert this to the longhand, this is that there will be parentheses around this one, and this is OR. The other one is x and not y, like so. So that's the really longhand version of not xy or x not y. Do we have any questions of the notation? Why in shorthand, in this format, is in longhand this particular format? Do we have any questions? Okay. All right. So if there are no questions, then we'll go ahead and evaluate. Okay. So if you do the evaluation when x and y are both false, then the entire disjunction is going to be false, because on either side at least there's one non-negated x or y, and that one is going to give us a false for the conjunction. So when we have false or false, then the entire thing is false. In this case, we already okay, I just turned on the caps lock. So let me undo a few things. Okay, so get back to here. All right, so when x is false and y is true, we already know that the left-hand side of the OR is going to give us a true. So that means the entire OR is going to be a true. On the third row, we know that we have x being true, y being false. But we also know that in this case, x and not y is going to be a true, so we'll give the whole thing a true. And then in the last one, they are both true, so that means not x is going to be false, not y is also going to be false. And the first conjunction term has a not x in it, so it has to be false. The second conjunctive term has a not y, so it has to be false too. So we end up with false or false, which means the entire result is false. So, okay, so now we look at this expression here, and then we ask, can we do this using only transistors? What do you guys think? It's not as obvious as the previous one, but can we? Okay, I'm not even counting transistors. We can use as many transistors as it takes. The answer is yes. Okay, Well, not anything, okay? Not anything is possible. But in this case, it is possible because we broke everything down to logical NOT, logical AND, and logical OR. And we already know how to do these three logical operations using just NAND gates. And we also know how to implement a single NAND gate using only 4 transistors. So that means, oh, we can do this, okay? You know, as clumsy as it seems, we can do it using only transistors. Are we good so far? So what is the implication of all of this stuff here? Okay, so let me summarize, what is the current situations that we are in. So now we can say, whoops, in base 2, we know that the CXY is really just X and Y. Yep, well, yes, we can. We can, not quite a calculator yet, okay? We can make an adder, okay? But an adder is not a calculator. RXY is not XY or X not Y, okay? So that's what we know, okay? So in base 2, we do not need to resort back to the mod operator. We don't need to refer to addition. So this addition symbol over here does not mean addition at all. It means disjunction, okay? So we are converting everything into Boolean operations. And we know that all of the Boolean operations mentioned here, they can all be done using transistors. So now we want to look at how we can structure these gates in order to make an adder in base 2. So I think this is pretty exciting because now we say, oh, okay, we can indeed use a whole bunch of P and N transistors to perform addition. So the only thing that we haven't been introduced yet is how do we structure the connections between these gates, okay? So that is one part that we haven't talked about yet, okay? But does everybody see the bigger picture of what is the significance of the last 2 lines on the whiteboard? I mean blackboard, chalkboard. Have to be, yeah. All right, so, okay. Now, let's get back into base 10, okay? Because we know how to perform multi-digit addition in base 10, so we want to analyze that process, generalize it to whatever base we choose to use, then apply it to base 2, okay? So that's where we are going, okay? We are gonna go back to base 10, so just so that we remind ourselves how to perform multi-digit addition in base 10. So I'm gonna give us a number like 968, okay, plus, oh, let's give it 033, okay. All right, so we look at this and go like, okay, that doesn't sound too hard. I mean, I know most of you can do this without using a piece of paper nor a calculator, okay? I cannot see what you're doing. I hope you're not using a calculator to figure out the answer to this one, okay? All right, so how do we do this? So most people will look at this and start with the least significant digit, which is correct, right? So 8 plus 3 is a 1, but then we have a carry to the next digit. So we have 6 plus 3 plus the extra 1 as a carry. So that ends up as a 0. But it also has a carry to the next one. So this is 9 plus 0 and then plus the 1. That is the carry. Okay, let me just use this as a carry. So now this one is also a 0. And then 9 plus 0 plus 1 has a carry of 1. So we end up with a 1 over here for the thousand place. So now we have 1001 as the result of adding 968 to 33. Shocking? Yes? No? Maybe? All right. So I think most of you know how this works, right? In base 10, we know how to perform multi-digit addition in base 10. So what I'll do next is to rewrite the same addition, but using a different format. So I'm going to use 968 plus 033. Okay, but this time I am going to have one row that I'm going to call, this is the Q row, and then there's another row called the K row. Okay, and we have a second addition. So all I am doing, okay, so Q, so let me just describe what Q is, okay. So Qi, okay, or digit I of the row Q is by definition just R of xi, yi. And this is row, this is x, this is row I, this is row, excuse me, I take it back. The first one is x, the second one is y, and this is row Q, and this is how Q is defined. X0 is referring to this 8, x1 is referring to this 6, x2 is referring to this 9, and similarly for the y digits. Okay, we got a question coming, so let me read the question and answer that first. All right, so I thought there was a question coming. Maybe it's not a question. All right, so that's what Q is. Okay, so when we look at this, okay, we say what is the single digit result of adding 8 and 3? Okay, it's a 1. Put a 1 here. What is the single digit result of adding 6 and 3? It's a 9. What is the single digit result of adding 9 and 0? That's also a 9. What about the k's? So the k of I, or I should say k of I plus 1, is the carry of the previous column. Okay, so I'll just say in quotes, okay, carry of column I. Okay, carry from. Okay, so carry from column I. So if column I somehow ends up with a carry of 1, then ki plus 1 is going to be a 1. So now we get back to the concrete example here, and then we ask, what should I put here? Is there any addition prior to digit 0 that might contribute a 1 where the cursor is at this point? Do we have any less significant digits to worry about? No. Okay, so if there are no less significant digits, then we'll say it's just a 0. Okay, and then we look at this particular carry bit here, and we ask, well, is there any carry from the previous column? When we perform the additions of the previous column, do we end up with a carry? So we look at the C of 8,3 and go like, yep, that's going to give us a carry of 1. So now we put a 1 over here. So now we look at this one, which is K2. So K2 is really asking, when we look at the column, when we look at column 1, does either one of those additions end up with a carry? Okay, so we look at the two additions. So we have the 6 plus 3. No, that one does not have a carry of 1. Then we look at the second addition. Okay, remember each column has actually 2 additions, because the second addition has to do with adding the carry to the partial sum from the original digits. Okay, so when we look at the second addition, we have a 9 plus 1, which has a carry of 1. So K2 also has a carry of 1 in this case. So let me get rid of this plus here, and we'll move it over here. So as it turns out, we look at 9 plus 0. Nope, that doesn't have a carry of 1. But when we look at this 9 plus 1 of column 2, it also has a carry of 1. So we actually put a 1 over here as well. So K3 is a 1. Do we have any questions about this notation? I know it is very different from what you are used to, because we are now using an entire row for the carries. but it doesn't really change the mechanism. It's just making it explicit that we have a second addition because of the carrying. So are there any questions? All right, so Aiden is asking or making a point. All right, so the question is this carry repo versus carry look ahead? We're not quite there yet, okay? So we're not looking at the circuitry where it will be pretty clear what carry repo is, but it is, in a sense, it is, because we cannot determine K3 until we have determined K2. We cannot determine K2 until we have determined K1, and we cannot determine K1 until we know that K0 is assumed 0 in this case. So the whole concept of carry rippling is already somewhat visible in this case, but not in the circuitry kind of sense. Okay, so when we convert all of this into a circuitry, then we'll see the chain of ripples, the chain of carrying even more obviously. But Aiden is correct that when we perform calculations by hand, we need to do the calculations from right to left. So we have to start with the least significant digit and then move our way to the left hand side one digit at a time. So that is because we need to ripple. All right, but we are not done yet, okay, because we haven't really calculated the sum. So as it turns out, the way we define the sum, SI, digit I of the sum digits, is really just the R of QI and Ki. In other words, it doesn't need to refer to a previous column. It just needs to look at the Q value and the K value of the same column, and then perform the single digit addition, and whatever the result is the answer. So now we have 1 plus 0. The single digit result of 1 plus 0 is a 1. Now we look at the single digit result of 9 plus 1, and that is a 0. We also look at the single digit result of 9 plus 1, which is another 0. And this one has an implicit 0 over here. So it's 0 plus 1, and the single digit result of that is just 1. So are we doing okay so far with this new notation? We have x as one of the numbers being added, y being another number that is being added. And then we use the square bracket in this case to indicate which digit we're referring to. So Q of I is by definition the single digit result of adding xi, yi. K, we're kind of thinking about how to phrase that, okay? Because there are two sources of carrying, okay? So we'll deal with that later. And then the sum, the S row, is S of I is really just defined to be the single digit result of adding Qi and Ki. All right, so we got some questions. Andy is asking, do Q and K stand for anything? Q doesn't really stand for anything. It's just one of the letters that is free to me, that I use. K is carry, misspelled, or German style. Yes. Deutsch style. Yeah. Okay, very good. So K is really just carry. But I don't want to use C because we already have used C as a symbol for the function. So I want to use K as the name of that entire row. All right. So let's take a look at the K term because we want to figure out, well, instead of using, just quotes to say that this is carry from column I, can we do better, okay? So we know that there are two sources of carrying, okay? So when you look at this one over here, it is coming from the carry of adding x and y, okay? So now we know at least one of the components is the carry of adding xi, yi. Then we look at this particular carry of 1, this one over here in column 2, and then we ask, where is that 1 coming from? Nope, it is not coming from the carry of adding x and y. It is coming from the carry of adding q and k. All right. So we now know that C of Qi Ki is another source. Okay. So now we ask, well, we got two values. What do I do in between to join these two or have an aggregate value when we want to have a result of one single value, but we have two sources? We have to somehow combine those sources. So at this point, we'll just say, well, a simple addition seems to work. Okay, so we'll just use a regular addition here. Okay, in fact, I'm gonna use the word add because sometimes I use the plus as an or, and other times I use add. So in this case, it is definitely just add. So I'm just gonna use the word add so that there's no confusion whatsoever. So are we good so far? Yes? No? Maybe? We're all good? Okay, excellent. So do you think the relationships between x, y, q, k, s would change because we decide to change our base from 10 to 2? In other words, does anything that we see here is specific to base 10? Absolutely not. Okay, very good. Okay, so if nothing about this is specific to base 10, then it will look exactly the same way in base 2. Okay, all right, so that means we can use the same mechanism. Okay, so we're going to do a base 2 addition by hand first, and then we'll go ahead and kind of generalize what the circuitry may look like when we want to work with base 2 only. Okay, so let's start with 1, 1, 0 in base 2. So now we're dealing with base 2 numbers plus, okay, I think that should be fine. So we'll have 1, 1, 0 plus 0, 1, 1. Okay, well, let's see, we can do this, change this to a 1 and change that to a that would be fine. Okay, so we will take a look at this one, and we'll label the rows exactly the same way. So we have, this is row X, this is row Y, and I have to emphasize that this is in base 2 so that we don't confuse the two examples. So we're gonna have another add here. This is our row K, this is our row Q, and last we have our row S. There we go. But remember, now everything is in base 2. So Q hasn't really changed its definition. Q is still the single digit result of adding X and Y in this particular column. So what should I put here where the cursor is? What is Q0 in this case? It's just a 0, okay, because 1 plus 1 has a single digit of 0. Okay, very good. And then K0 is usually assumed to be 0. Okay, even there are cases where it is not assumed, but we'll encounter those cases later on. So for now, we can just say that we'll assume K0 is 0. Okay, so the sum is really the R, or the single digit result of adding 0 and 0 in this case. So that's a pretty easy 0 down here. So once again, we have 1, 1. Okay, 1 plus 1 has a single digit result of a 0, right? So now we look at this carry here and ask, do you think K1 is going to look any different when we have base 2 as opposed to base 10? Just in terms of the structure of K1. Okay, it's going to look exactly the same, right? So, but now we have to ask the questions of, what is the carry of x0, y0? x0 has a value of 1, y0 has a value of 1. What is C11 in base 2? Remember, C is the same thing as conjunction, so it is a 1. Okay, so we put a 1 over here, and then we have 0 plus 1 is a 1. Okay, so put a 1 down here. 1 plus 0 has a single digit result of 1. So now we look at this carry bit. Okay, this is K2. So K2 is using the same definition that we have looked at here. So K2 is the C of x1, y1. All right, x1, y1 is definitely having a carry of 1. So we know K2 is also a 1. So now we have 1 plus 1, which has a single digit result of a 0. Okay, so now we look at this bit over here. Okay, because there's an implicit 0 over here, but we still have to look at K3. So K3, using this definition up here, is the carry of x2, y2. When we look at x2, y2, nah, that's not going to give us a carry of 1. But when we look at q2, k2, that will give us a carry of 1, because the carry of q2, k2 is one of the components that can contribute to K3 in this case. So K3 in this case, in the base 2 example, is also a 1. So we end up with a 1 over here in the sum. So are we good so far with base 2? You can see the process is exactly the same. It's just that we changed the rules just a little bit. Okay, the way we compute the single digit result R, and the way we compute the single digit, we compute the carry, are different compared to base 10, but otherwise the structure is the same. Are we okay at this point? Are we still good? Everybody still with me? All right, you're good. All right, excellent. All right, so now we look at this and go like, well, we only got one issue with this, okay? Because the Q of I is not an issue, because Q of I is the R, or the single digit result of adding xi, yi, and we know that that can be done in base 2, it can be done using exclusive OR, and exclusive OR can be done using just not, and, or, and we don't have a problem with that, okay? When we look at the sum, kind of the same thing, okay? You know, it's taking the Q bit and the K bit over here, but it is just using the R function, which we already also know is just exclusive OR. So that is not an issue either. When we look at Ki plus 1, we look at this and go like, well, we are partially done, but we partially is not done. In other words, we look at this and go like, we know the C function is just a conjunction, okay? That is not a problem. But this add is a problem, okay? Because it is an arithmetic operation. It is not a bitwise operation. So we have a little bit of an issue here. So now we want to look at the table, okay? So we want to look at this table over here. And let's see. We're going to look at this with x and y as independent variables again. And this time we are going to look at, I'll spell out the operators this time because I don't want the plus to confuse anyone. So on one hand, we want to look at x or y. On the other hand, we want to look at x and x plus y. Okay, so now we have two distinct expressions that we want to evaluate. One is a bitwise or logical operation. The other one is an arithmetic operation. So x can be 0. And when x is 0, y can be 0 or 1. X can be 1. And when x is 1, y can be 0, or y can also be a 1. So we still have 4 rows to this particular table. The first column, or the third column in this case, the OR column, is easy to compute because we know the only time we end up with a 0 is when x and y are both zeros. And then for all of the other rows, we end up with a value of 1. The plus column is pretty easy to compute too, because 0 plus 0 is really just 0. 0 plus 1 is a 1. 1 plus 0 is also a 1. And 1 plus 1 is a 2. So the OR operator will get us almost there. In other words, if I were to go back to the original definition of Ki plus 1, if I can replace this add with OR, I'm home free because we can do OR using transistors. I don't know yet how to do arithmetic operations using transistors because that's what we're trying to work on right now, right? So, but if I can somehow say that, hey, if I can just replace this add or plus using an OR, then we'll be good. So now the question is, can we? Okay. In other words, in base 2, can we define ki plus 1 to be, now I'm going to use logical operators, okay? So we're going to define it as xi and yi. That's just, the C function, which we have already talked about. And then the other side is qi and ki, which we have also talked about. So the key here is, instead of using plus, can we use or? That is the question. Okay, and I'm going to emphasize that this is our question. This is the question of the minute. Oops. Okay. So what we are really asking is, can the last row happen? Can this row happen so that the plus will give us a different result compared to the or? Okay, so when we try to answer the question, then we are really trying to answer, can this conjunction give us a 1, and at the same time this conjunction also give us a 1? Because if that case can happen, then we cannot change the plus to or. But if we can guarantee that that cannot happen, then we can just go ahead and go like, woohoo, we can cheat a little bit here. Instead of using the plus, we replace it with an or, then everything is binary, or everything is logical, and we are home free. All right, so Tom thinks it will work. So now the question is, can we prove it? Now this is CISP310, it is not CISP440, so formal proofs is not super duper important, okay? Not from your perspective, but from my perspective, it is still really important, because I think it is important that I can show you that we know 100% that this can be using a or. It's not just that, yeah, I think we can do that, okay? No, we know for sure that we can do it, okay? All right, so let's look at all those cases. So what do we know if we assume xi and yi is 1? Okay, and I am going to put parentheses around this, just so that we know, we are making, what is the assumption, okay? The assumption is, what do we know if we know that xi and yi has a result of 1? What do we know? Come on, you guys can try to do some inferencing here, okay? So I'm gonna say xi and yi, whoops, is 1, whoops, I cannot type today, is 1, is implying what? What is it implying? Okay, first of all, can I look at this and say, hey, I now know what xi really is and yi really is? Exactly. Okay, so Daniel has got it. So we know that xi is a 1 and yi is also a 1. All right, so from that, what can we infer? Think about the definition of Q. How is Q defined? Q is defined as the single digit result of adding x and y, right? So if I already know what x really is, it's a 1, and I know what y is, it's a 1, what is the single digit result of adding x and y? It's a 0. Very good. So Q of I is known to be a 0. If I know Q of I is a 0, what do I know about the conjunction of Q and I and whatever? Okay, what do we know about that? It's going to be false. Exactly, because if at least one side of a conjunction is false, the entire conjunction is false. So we know that xqi and ki is also a 0. Ooh, this is nice, right? So we have solved 1/2 of the case, okay? Because now what we have done, is we have just using logic, we have just proven that when I'll kind of graphically do it here. If we know that this term is a 1, it is guaranteed that this term is a 0. That's only 1/2 of the cases, right? Because what about the other way around? What if knowing this term is a 1, what can we know about this term over here? Okay, so we want to know that too. Okay, so now we go ahead and work on that second case. So now we ask, what do we know if we assume Qi and Ki is a 1? Same deal, okay? So we say, okay, because it's a conjunction, if the result of a conjunction is a 1, that means every single component of the conjunction is a 1 as well, okay? So we say Qi is a 1 and Ki is also a 1. Aha, okay. What can cause Qi to be a 1? Okay, so Qi being a 1 implies what? There are two possible cases, right? If we want to look at the actual value of x and y, there are two cases that can make Q of I a 1. The first case is xi being a 1 and yi being a 0, okay? Or the second case is xi being a 0 and yi being a 1. Are we okay so far? Just knowing that Qi is a 1, we know x and y are opposites to each other. Is that okay? Okay, so we are good with this. Why is this important? Okay, so we now say it also implies, okay, that K of I is what? Actually, let me track. Yep. So we know x, y when, oh, okay, there we go. So now the question is, what about the conjunction of xi and yi? I asked the wrong question. I asked, what do we know about Ki? We already answered the question, right? So what we want to know is, what about the conjunction between xi, yi? It has to be false. Very good. Okay, very good. Andy, Quan, you guys are both correct. Xi and yi is going to be false. Whoa, hold on a second here. This just finished the second half of the proof. Because what this is saying is, if we start with this side, or the right-hand side of the OR being true, it guarantees the left-hand side of the OR being false. I think we have just proven that we cannot have a case of both sides of the OR being true. Because we already said what happens when xi and yi is true, then this side cannot be true because Q of I has to be a 0. Then we ask the question in the opposite way. We ask, what do we know if we know this conjunction is true? Then we also know this conjunction is going to be false. So that means they cannot both be true. Okay, when I said both, I'm referring to the left-hand side of the OR and the right-hand side of the OR in the proposed revised definition of Ki plus 1. It is really nice, okay? Now, if you're wondering why Daniel just wrote down, oh, this is really nice, it's because we can now legitimately replace the plus, which was between these two operands. Remember, this was a plus before when we were working with base 10. Now we can use logic and legitimately just say that, yep, we can replace that plus with an OR because both sides being 1s cannot happen. In other words, when we look at the table, okay, when we look at this table over here, the only case that differentiates a OR versus a plus does not happen. It is nice, right? I mean, Tom, this is nice. It just works out, okay? So now that we can use the revised definition of ki plus 1, we can now actually do everything using logic gates. Because the definition of k, of ki plus 1, now I know it is still a handful because we have 2 and 1 or, and it relies on the previous k, but it's okay. We can actually, make a circuitry to do this calculation. Yep, so this is an ideal situation because now we can say, oh, to perform addition in base 2, we can rely on just transistors. We know how to structure transistors to perform addition in base 2. This is where we go like, woohoo, yes, cool. Fireworks, right? They cannot be 1 at the same time, regardless of the base, actually. And that's kind of the beauty of the whole thing, is we could have used OR even for base 10, because they cannot be 1 at the same time. So the right side is never true. Nope, the right side can be true. It's just that if this side is true, then we know the other side has to be false. All right. So so I'm going to wait until Daniel is finished typing, and then I'll pose another question. All right, so Daniel said, my question was about it being true. How can both Q and K be true? Because this K relies on the column of I minus 1. So how this K can be true is not something we can observe from column I. It has to be coming from column I minus 1. We know this Qi can be true because X and Y just have to be different for column I. But K in column I being true has to do with the arrangement of column I minus 1, which is not in this equation. So from looking at this equation, we cannot see why Ki can be true. All it takes is Xi minus 1 and Yi minus 1 both being 1s, then Ki is a 1 already. So we know how to doctor and make that happen, but exactly why Ki is 1 in a particular case, we cannot tell from this equation. Okay, very good. All right, so now if we take a step back, in other words, we have been just playing with a whole bunch of pine needles, until now. So if we take a step back and look at the pine tree, okay, what have we learned? Okay, well, we have learned that in base 2, we can use logic gates to do everything. Okay, we can perform addition without using arithmetic operations, without using arithmetic concepts. Okay, we can rely on just Boolean or logical operators to perform addition when we're dealing with base 2. So someone is going to say, well, big deal, okay? What can you represent in base 2? It's just a whole bunch of zeros and ones, right? I mean, it's not useful. So now the question is, do you remember what we did in the previous class? I know it's a long time ago, 5 days, right? 120 hours. That's a long time, okay? We did base conversion, didn't we? Okay? So what base conversion has taught us is any value can be represented using any base. So that means any value can be represented in base 2. And now that we can perform addition in base 2, that means we can add any value. We can find the sum of any two values because we know values can be converted to be represented in base 2. And now we know how to perform addition in base 2. We can now basically compute the sum of any two values. Now this is big, right? This is really, really cool. So we are almost running out of time. There are two things that I need to do. The first one is there is a new lab for today. Yeah, Tom, isn't this cool? Usually by this time in an actual face-to-face class, you'll see me being super happy and super excited because, wow, we can do everything with transistors. And transistors are getting smaller and smaller. This is all cool. But since this is not a face-to-face class, you don't get to see nearly as much excitement. Okay, so let me get back to the things that we need to do, right? Okay, I almost distracted myself to the point where I do not remember what I need to do. Okay, so the new lab of today is base conversion. It is due on the 3rd, which means you have a little bit less than 2 days to work on it. There's not really a whole lot of point values, but it does help you exercise what you have learned about base conversion. So my recommendation is to do it like right after this class. You'll take a 10-minute break and then start working on this lab. It's not long. Get it done, get it over with, so it doesn't hang over like a ghost, okay? That's one. And then it has a passcode, okay? So base conversion has its own passcode. So I'm going to write this one down in Discord too. I think it is octopus. Okay, so I'm just going to type here. The code of the lab is octopus. Yeah, it was octopus because in previous classes when I was trying to explain why anyone would use base 7 would be octopi. So octopi would use base 7. And then you guys would say, but octo means 8 tag, we know that octo means 8. Well, I know that too. But I also know that octopus likes to get drunk. So it needs one tentacle to hold a can of beer. So it only has 7 for counting purposes. So that's why octopus would use base 7. And then somebody else is going to say, but octopus cannot drink beer because it's underwater. Well, I beg to differ. Have you guys ever watched SpongeBob? There we go. We got the perfect logical explanation of how to drink beer underwater as an octopus. All right, so now you guys got the 3 things that I want you guys to do. Number 1, okay, finish the roll taking activity. The passcode of today is Ripple, R-I-P-P-L-E. 2, work on the lab of base conversion. The passcode is octopus. 3, read ahead of me. So even though it sounds like, wow, we are done with binary addition, well, let me show you the notes because you guys would like this. So in terms of the module, we are now down to, I think it's section 6. Yep. All right. So we are now down to section 6. Okay, everything that we have talked about are covered in section 1 to 5. So this is section 6. Section 6 doesn't sound like a whole lot, right? Because all it says is, but wait, there's more. But if you watch any infomercial, you know that when they say there's more, there's a whole lot more. There's free shipping. You're getting another set for free if you buy 3 more, right? And so on and so forth. So if you just kind of scroll down, you will see something go like, whoa, what is that? That is Boolean algebra, okay? It's Boolean algebra, which I'll explain. You do not need to learn Boolean algebra in this case, okay? It's not the purpose of CISP310. It is the purpose of CISP440. So if you have not taken CISP440, this may be a good chance to get a preview of Boolean algebra. If you have taken CISP440, this may be a good chance to review Boolean algebra. So either way, I don't think it will hurt, okay? So there's a whole bunch of derivation, and then we get to this portion. This is the good part, okay? if you ignoring how we got to this conclusion, okay, we can see K3 originally needs to know what is K2, but using some Boolean algebra magic, okay, we now reduce it to something that does not contain K2. So K3 can now be determined using a whole bunch of P and G terms and just K0. And the P and G terms are really easy. One is the AND of the X and Y, and the other one is the OR of X and Y. So they're pretty easy to compute, no problem. Okay, but the idea is there's no chain requirement anymore. K3 no longer relies on K2, K2 no longer relies on K1, K1 still relies on K0 because everybody relies on K0, okay? But because of this, this is also called carry look ahead. But because of this mechanism, when you want to make an adder for 64-bit numbers, the adder can now be, in theory, as fast as a 2-bit adder. Whereas before, the 64-bit adder is going to take 32 amount of time of a 2-bit adder because it is linear to the number of bits. But using this technique that we call carry look ahead, using this particular technique, it is now becoming constant time. Okay, it doesn't matter how many bits you're adding. 128 bits, no problem. 256 bits, no problem. They will take the same amount of time. Okay, so we'll talk about this magic on Thursday. Okay, so on Thursday, this is what we'll be concentrating on. So I do want you guys to read ahead of time, even if you don't fully understand the derivation. It's okay. Okay, just kind of get the big picture when you're reading, and then when we are in class, then I will explain the actual Boolean algebra used in order to work on that derivation. All right. So I am done with lecture material. I just want to see if there are any questions before I turn off the live stream. No questions that I can see. All right, cool. So you guys know what you need to do. 3 things. Okay, I know I'm sounding like a dad because I am. So we got attendance, the lab, and reading ahead. Not just carry ahead, reading ahead too. So yes, Arrival was an excellent movie, wasn't it? Yep. All right, cool. So I'm gonna stop streaming, but I'll still be around on the text channel, and I'll help Mustafa reset his or her quiz. Alrighty.